Now, if you remember from before, we said kinetic energy is equal to 1/2 mv squared. And from last class, if you remember, V equals R times W. Relationship between linear versus angular speed. So now the kinetic energy can be written as 1/2 m. Instead of V, I'm going to put R, W, and you square it. So you end up with 1/2 m R squared times W squared. I'm going to take mr squared and talk about something called inertia. Inertia is defined, and that's really based on what the object is made of, like the mass of it. What is it made of? The inertia is defined as the summation of m times r squared. So for example, if you have a pen and you want to find the pen, the inertia for the pen, basically what you want to do is slice that pen into thin pieces. You say, what are you going to spin this pen? I'm going to spin it around the center or around the edge. If you're going to spin around the edge there, so you want to cut it into small pieces and say, okay, the mass of this piece times the distance to that pivot point squared, plus the mass of the next piece times the center from the distance from the center to that pivot point squared. So if I have a rod like this, and I'm spinning this around this point, I want to find the inertia for that. I'll slice it into thin pieces. For each one, I'll take the mass of each piece, like this piece, the mass of it, multiplied by the distance from here to here squared, plus the next piece, plus the next piece. You grab every piece, the mass of this times the distance from here to here squared, plus this piece, the mass times the distance from here to here squared, and you add them all. That's your inertia is. So since this is actually what inertia is, so I can write the kinetic energy is 1/2 inertia times W squared. Notice mr squared. Mr squared is the inertia. So that's the definition of rotational kinetic energy, Kr, due to rotation. 1/2 times the inertia times W squared. Now, to calculate the inertia, again, you're not going to be able to take a ruler like this and slice it into thin pieces. Well, no, you can't. But you find the mass of each one times the distance squared, the mass of the next piece times the distance squared, and add them all. Well, somebody did the work for us, did the math for us. And they said, based on the shape, we can tell you what the inertia is. And there's a chart for different shapes what the inertia will be. If I have a ring, like a wedding band ring, that's this one, a hoop there. The inertia for that is m times r squared. If I have a disc, a solid disc, not a hoop there, and you're spinning that around the center, the inertia will be 1/2 mr squared. If you got a solid disc but not spinning around the center, spinning around the edge there, it's 5/2 mr squared. If I have a ruler and I'm spinning that around the center, I'm turning this around the center of it, the inertia for that 112 ml squared. If I have a ruler that spins around the edge, the inertia for that, it's 1/3 ml squared. Hollow sphere like a basketball, that's 2/5 mr squared. Solid sphere like a bowling ball, 2/5 mr squared. That was 2/3 here. Solid sphere that rotates around, not the center, but on the edge there, 7/5 mr squared. And if you have like a rectangular shape, 112 or square, 112 ml squared, 112 ml squared, that's rectangular shape, L squared plus W squared. So different shapes have different inertia. Somebody calculated that for us. If we give you a different shape than this, then we have to calculate the inertia ourselves by using the summation of mr squared. So if I give you, for example, an object that looks like this, I got a 2 kilogram here, and I got a 1 kilogram here, and they're spinning around this point. They're spinning around this point. Like somehow they're attached together, but they're spinning around this one, around that pivot point. Let's say this distance is 0.5 meter to the first one, and 1 meter to the second one. Then the inertia for that is going to be the summation of mr squared, which means we take the mass of the first one, that's 2 kilogram, times the distance from here to the pivot point, and that's 1, and you square it, plus the inertia of the second one, which is 1 kilogram, times the distance from here to here squared. So that's 2 plus 1/4, that's 5, or no, not 5, what's that, 9? 9 over 4? So the inertia is 9 over 4. Usually you're going to be given one of those shapes for these problems, the one you looked at, either a ring or a sphere, or or it's going to be a disk there, and go through it and calculate all the stuff we need to calculate. So let's take an example here and see what's going to happen. We actually have a dumbbell shape there. If you go to the gym, you know what they look like. You got a piece of weight here, you got a piece of weight here. They're connected with the rod. We're going to spin this in this direction. The masses on the end usually are equal masses. And if I call that distance from here to there is r, then this is r too. So from this point to that point is 2r. Now if I use this point, if I spin them around the center, right there, what is the inertia? I'm neglecting that beam that connects them because I don't have a mass for it. Just these two. The inertia will be what? If I use that point right there for the pivot point. That's my pivot point right there. So I'm going to spin them like I'm holding a ruler on my finger, and I'm spinning that ruler like in the middle, like baton. You see that in parade. The person holding them, spin them like this, in the middle of it. The inertia will be the mass of this times that distance squared, plus the mass of this times that distance squared. What's the inertia for that? 2 of them. But what happens, the same one now, instead of spinning around the center, I'll spin around this one. I'm grabbing from the end. So I'm going to spin it right there. That's my pivot point right there. What's the inertia? Is that different? Well, the inertia for that It's the mass of this one, m, times the distance from the center to that pivot point, which is 0, plus the mass of that, which is m, times the distance from here to there, which is what? 2r, and you got to square it. What's your inertia now? 4mr squared. So it depends where you spin it. The inertia will change from point to point. If I opted to do one more time, but this time, instead of spinning it right in the middle here, I'm going to spin it 2/3 of the way, or 3/4 of the way. So this is r here. And this distance is r over 2. So that's my pivot point. So the inertia for that will be what? The mass of this m times that distance squared. What's that distance? That's half an r. Plus the mass of the second one. And what's the distance from here to here? This is r plus half an r. That's 3 over 2, 1.5 r. So notice the same dumbbell have different inertia based on what I spin it. This is 1/4 mr squared plus 9 over 4 mr squared. And you end up with what? 10 over 4? Or by 2, is that 5 over 2? 2.5 mr squared. So that inertia change is based on where that pivot point is, where you're spinning that. Now, I started talking about the Science Museum in Boston last time, and I talked about if you have a disk, because they do this experiment there, but if you have a ramp like this, we'll give it some dimension here. Here's what we have. We have two things. We're going to put a disk, and we're going to put actually a ring. The first one we'll do is a disk, a solid disk. So the inside is filled. It's a thin disk. So I'll even write at the top with a disk here. Like a CD. I was trying to think, like I'm looking around to see if I see anything. A thicker CD. That's a disk. It's full on the inside. You put on top of that, do you have any values, height and everything? And the other time we're going to do the same experiment, but instead of a disk, we're going to put a hollow ring, a wedding band. So that's a hoop there. Hula hoop. Now, does the disk reach the bottom before, after, or the same time as the hoop? That's what we try to find out. Let's say the height is h. The mass is the same for both. They both have the same mass. We don't know what the mass, but assume they both have the same mass. Which one reaches the bottom first? Now, assuming as they went down, they weren't slipping, because if you're slipping, we have a problem there. Nothing was slipping, no friction, neglect friction. Here's a big neglect friction. Okay. Let's look at it now. If you neglect friction, we have the mechanical energy on the top is equal the mechanical energy at the bottom. If you take all the energies, potential and kinetic at the top should equal potential and kinetic at the bottom. They should be the same. Okay. Now we put the disk there, it wasn't moving. So what we have on the top is potential energy. How big? The mass times gravity times the height. The kinetic energy was what? 0. When you get to the bottom, if I use this as reference, what is your potential energy at the bottom? 0. What is your kinetic energy at the bottom? Is the thing moving? Absolutely. But we have two kinetic energy. We have 1/2 mv squared, because this will be coming down, velocity v. At the same time, what's happening? That thing is spinning. Has kinetic energy due to rotation, which is 1/2 I w squared. Now, I need to go to my book and look at the inertia for a disk, a solid disk. The inertia for a solid disk that spins around the center is 1/2 mr squared. The radius is the same for both of them, by the way. So the inertia, it's 1/2 mr squared. That experiment at the Science Museum, the disk and the hoop have exactly the same mass and the same radius. So if you plug them in, you have mgh equals 1/2 mv squared plus 1/2, in place of the inertia, let's put 1/2 mr squared times w squared. Mass times gravity times height equals 1/2 mv squared plus 1/4 mr squared w squared. mgh equals 1/2 mv squared plus 1/4 m r times w squared. What is r times w? Wasn't that v? V equals r times w. So that's actually v. And notice the m shows up in every one of them, so mathematically I can just take my pen and get rid of it. Gravity times height equals, what's 1/2 plus 1/4? Is that 3/4? Multiply by 4/3 to get rid of the fractions. And what is v equal to? The square root of 4/3 times g times h. Now, if I give you the height, if I said the height is 1/2 meter, I can plug it in, there's my answer. I'll leave it in terms of h. Now, as I said, they take the hoop and the disk and they put them next to each other and they roll them, and they're trying to ask you which one gets to the bottom faster, which one's moving faster when it gets to the bottom. This is the velocity of this when it gets to the bottom. Well, what is the velocity of the hoop when it gets to the bottom? Is it larger or smaller? So let's repeat the process now with the hoop. This one with the disc, the solid disc. Now repeat the process with the hoop and calculate the velocity for the hoop. Same mass, same radius, same table. The height is the same. The mass is the same and R is the same. Again, neglect friction. We have conservation of energy. The potential and the kinetic at the top should equal the potential and the kinetic at the bottom. The mass is the same, gravity is the same, the height is the same. Kinetic energy is 0 at the top. This is my reference for the height. The bottom, potential energy is 0 because there's no height. Kinetic energy is the 1/2 mv squared plus 1/2 IW squared due to moving down in this direction, that's this one, and also spinning, that's this one, rotation. But the inertia is different here. The inertia for a hoop, for a disc, is actually 1/2 mr, for a hoop is mr squared. Now 1/2 is mr squared. I know I wrote this stupid. This mv squared looks like m to the power of v. So it's mgh equals 1/2 mv squared plus 1/2 mrw squared. R squared w squared. That's a v again. The m cancels each other out. It shows up in every one. V equals the square root of gh. Which one has a larger velocity? This one or the other one? Notice the other one has a velocity 4/3 gh, not 1. This is 1. This is more than 1. So the velocity of the disk is higher than the velocity of the hoop. Velocity of the disk is higher than the velocity of the hoop. The reason? Less inertia. Less inertia on the bottom. As spinning there, which will make the kinetic energy on the bottom larger. This one has more inertia as spins, which makes the kinetic energy, translation of kinetic energy actually less, and that's why your velocity is smaller. Next time you watch a short distance bicycle race, look at the back wheel of the bike. It's a solid piece. It's not a hoop there. Most bikes have a spokes and you have a ring there. You have something like this. But for short distance, they use these bikes here and a track there because that gives you actually bigger speed, less inertia. So now you can't neglect. Remember in the lab when we had the weight dangling from the pulley works as a hoop there. It has inertia. We're going to lose kinetic energy to that for being spinning there. I said neglect at that time is not going to be much because the mass is really small on them and it's not moving that fast. But the truth is you lose energy, and the kinetic energy due to rotation is 1/2 IW squared. If you have a pulley that looks like this, just an idea. and you have a couple of things to support it like this, and you're trying to find what is the inertia for that pulley. Well, you have to look at that as three separate pieces. The three separate pieces for the pulley is the outside ring, then you get this beam here, then you get that beam. So there are three things making that pulley there when you look at it. That's how we make them. We take a beam like this, and a ring like that. We put this here, we put this one there, and you end up with that. So if you want to find the inertia for this one, it's the inertia for this plus the inertia for this plus the inertia for that. So if I want to calculate the inertia, I really got to dismantle that, take the mass of this one, and measure the radius. The inertia for a hoop here is what? The mass of the hoop, inertia, is equal to mr squared for this one. It's the mass of this one, this is r, whatever the mass of that hoop. The inertia for this, it's a rod that spins around its center there. The inertia is 112 ml squared. Inertia is 112. I gotta take the mass of that. I don't know what the mass, I gotta weigh it, put on the scale, but I know the distance from here to here is what? 2r. Whatever r is, that's twice that, because that piece goes from here to here. If that's r, this is r. The length of that is 2r. And the inertia for this, it's 1/2 ml squared again, which is 112, not 1/2. 112 m times 2r, and you square it, and you find this number, and that number, and you add them, and that's the inertia for your pulley. If you get 3 of these or 4 of them, you find it for 1 multiplied by 4, because you get 4 of them. Here you get 2 of these. So you find the inertia for 1 multiplied by 2, 1 for this beam, 1 for that beam, plus the inertia for that. What happens if a fly goes and lands right here on it while it's spinning? A fly. You got to find the inertia for the fly, which is the mass, inertia is mass times r squared. The mass of the fly times the distance from here to there squared. You got to add that to that pulley, and that becomes the inertia for the whole system. As I said, most of these problems, they're going to give you the inertia. Every once in a while, they give you a problem. They go, you know what, we got a merry-go-round that looks like this. It has a mass of, 200 kilogram. It has a radius of 5 meters. Well, we know the merry-go-round is solid. It looks like a solid disk. So the inertia for that is what? For a solid disk, the inertia is 1/2 mr squared. The mass is 200. R is 5 squared. 25 times 100, that's 2,500. By the way, if you're curious about the units for inertia, the mass is what? Kilogram. And the radius is in what? What's the unit for distance, radius? Meter, kilogram, meter squared. But wait a minute, what happens now if a 75 kilogram boy or man goes on that merry-go-round, stands on it? 75 kilogram, and he is 4 meters away from the center. So a person just got there and stood on that one while it's moving, spinning. What's the inertia now? The inertia no longer 2,500. It's the 2,500 plus the inertia of the person, which is what? 75 mass times r squared. And r is what? 4 squared. So the inertia now is 2,500 plus 16 times 75, 1,200 is now 3,700 kilogram meter squared. The inertia changes. If I know this is spinning, W is 5 rad per second. I can tell you how much kinetic energy due to rotation this one has. It's 1/2 I W squared. It's 1/2 I now is 3,700 because you have a person standing on it, times W squared. W is what? 5, and you square it. And that's 46250 joules. It's energy, still in joules. 46,250 joules. That's the kinetic energy due to rotation. Do you feel that? Yes. If you try to stop it with your leg while spinning, you stuck your foot there, it will break your leg. Where is that coming from? The energy that's moving, spinning. It's a big machine. It's 275 pounds or kilogram. That's about 700 pounds spinning at a decent speed. If it hits your leg, trust me, you're in trouble there. All the examples before, we neglected the pulley. So I'll do one where I'm not going to neglect the pulley. And this is spinning wheel. We did one just like it yesterday. I think if I pull my notes from yesterday, you look at them, you'll see that I talked about deadliest catch when they pulled that lobster or the king crab from the bottom of the ocean. So we have a block of mass M. This is the block of mass M attached by a rope to a pulley. We throw on top of the pulley. The pulley actually has a radius R. In the past, we neglected that. We didn't care about the radius. And it was spinning in this direction with angular speed of W. And once you attach the weight, as I said before, this was spinning and there is no engine attached to it to keep it spinning. Deadliest catch, you always have an engine that keeps spinning that thing even when you attach the weight to it. This like somebody took a bicycle wheel, hit them with their hand till it starts spinning, attach a rope to it, to the rope you have a mass there attached. So it's going to slow that wheel down. It's going to, this one rise up, move up there, up to a certain point, then it's going to stop. Velocity is 0. W now is 0. So once you hook that block, this is going to move up with the velocity v, initially upward. Here the velocity is 0, it's not moving. To what height does the block rise before coming to a stop there? We're not looking for a number. We're looking for an equation to solve that. Now, this is the before, that's the after. Let me label them. Before, after. The pulley is a solid disc. It's not a hoop there, because that's the inertia. I'm going to use this as reference. What I'm looking for, how high does the weight rise? What's that height? Again, neglect friction, no slipping there. We have conservation of mechanical energy. If you take the potential and the kinetic before, should equal the potential and the kinetic after. Again, when I say the word kinetic, I'm talking about both. This one has kinetic energy moving up, 1/2 mv squared. This one has a rotational kinetic energy. So mgh plus 1/2 mv squared plus 1/2 iw squared. These are the initial ones, the before, equals mass times gravity times final height plus 1/2 m v final squared plus 1/2 iw squared. Kinetic energy of this one moving up, kinetic energy of this pulley spinning. Josh is out 10. Vinny, don't tell me who sits next to you. Who sits next to you? Oh, Edelyn, the back there. Or just Vinny's the only one. I mean, Josh. So let's look at the initial one. If I use this as reference, the height is 0. So that potential energy is 0. 1/2. When I say mass, there's different masses. The mass of this and the mass of the pulley. Let's differentiate between them. Let's use capital M for the mass of the pulley there. And the mass down here is little m. So it's 1/2 m times the initial velocity squared plus 1/2. What's the inertia for a solid disk? Go to that page there. A disk is 1/2 mr squared. Capital M, the mass of the pulley here. Let me simplify this while I'm at it. 1/2 m initial velocity squared plus 1/4 capital M, different mass, r initial velocity, angular velocity here, speed squared, capital M, that's v squared. So if you factor v squared out, you have what? 1/2 m plus 1/4 capital M. If you want to factor that out. Now, let's look at the after. This block moved up h height. So potential energy is mass of the weight here, the little m, not capital M, gravity times the height, plus, now this is no longer moving, so the kinetic energy is 0, and the rotational kinetic energy is 0. It's not moving. That's it. Can we calculate what h is now? Again, if I gave you numbers, this won't be bad. So if I told you what the mass of the pulley and the mass of the weight we hung there and the initial velocity, you have an answer. We can tell you how high it's going to go. And that's the last piece of the chapter.